Okay, so previously I showed you that speed of light is the same in all inertial frames, but it was more or less just an experimental result. And now I would like to explore more of its consequences. Um, I would like to show you a simple way to prove that the interval, space-time interval between uh, any two events it remains the same in all inertial frames. That's invariant and what's called Lorentz transformation. So let me do it. Mhm. Okay, so first of all, what have we seen in the previous video? Yeah, that um, if we have um, a light ray traveling from the emitted, say, at moment zero and coordinate zero, and received somewhere here at time t coordinate x, um, then we know that x is equal to ct, right? And um, that's true in any inertial frame. Um, So if you see the same event in the movement system, we have the same equation for the coordinates describing it. Mm. I guess if we are in 3 dimensions by x, we mean like absolute value. Now, so it could be expressed differently, right? That this equation um, remains um, the same in all inertial frames. From here, I would like to show that such quantity um, which is called interval between two events, let's say occurring at time t1 with in location x1 and time t2 location x2, that this quantity t square t2 minus t1 square minus uh wait, sorry, it doesn't have to be zero. This quantity, let's call it s squared, um doesn't depend on the choice of inertial frame. That for different inertial frame it will be the same. So I learned like a nice trick. Mhm. how to show it. Here it is. It exploits what's called the radar coordinates, which I think is kind of very neat thing. So I would like to share it with you. Um, so let's look at our um, space-time diagram. This is our time coordinate. Let's say this is our space coordinate. And for simplicity, I will be working in a 1+1 dimension. But you could introduce it in 3 dimensions as well. Um, Now, here's how we actually become aware of some distant events from us. Let's say we are an observer who moving was just standing here at x0 all the time. And the way we learn about any event is that we send light signals at every moment of time. Yeah, so this is like in coordinates CTX, the light rays travel at 45 degrees lines, right? Whenever the light ray hits some object, it reflects back. Uh, and then, we measure this reflection at some point later in time. Okay, let me, for example, consider this event for simplicity. So let's say we emit a signal at time we call E, and then we received it at time R. So this times E and R uniquely characterize the position and the moment, position of the event and the moment at which it occurred, right? Uh, because indeed, if this is um, coordinate of the event, x, and this is its time, t, we see that x is equal to r minus e divided by 2, 1 over c, right? Because this distance is by definition the same as this distance, and this is just this. Mm, Okay, and the moment of time is just half a sum of r and e. Okay, that's kind very convenient new coordinates. Now let's consider um, two different inertial frames. So we'll have Alice and Bob. Um, Say Alice is just standing, so that's her world line, point 0, and Bob is traveling with some velocity, like this. Now, imagine they communicate with each other using light signals. Uh, So let's say every interval, small interval of time, dt, um, Alice sends a light signal to Bob, like this. Then we see that basically because of Doppler effect, Bob is receiving the signals with different intervals. Uh, Time factor k times dt, right? Okay. Now, um, let's ask a question. What happens if Bob sends signals to Alice? Again, in some intervals of time, like this. Let's choose this exactly these intervals. Then we see that she'll be receiving them um, with intervals of time stretched even more by a factor of k. We see that this factor k is the same because um, these two systems are actually equivalent between each other. There is a full symmetry. It's easy to see if you just rotate the system like this. Um, you see that, just if you rotate it this direction, then they're just completely symmetric. So this factor k and this factor k are the same. Now, let's imagine both Alice and Bob are looking at some event. Mm, try to draw it again. Let's pick this event somewhere. Let's say, okay, let me try to draw it here. Yeah, like this. Okay, so that's how it's seen by Alice using her radar. We call this the time EA at which she should have emit the light ray to see this event. And we will call this point RA as the moment when Alice will receive a response. And okay, and this line we will call correspondingly EB, because that's when Bob sends his signal to detect this event here. And this here is longer line, this whole segment we will call RB, because that's when Bob receive the signal back, right? Now, using what you already learned with these stretching factors, we see immediately that EB is K times EA, right? And also we see that A is K times RB. Yeah, like this. That just how the geometry look like. And from here it follows that if you multiply, say, one equation by K, um, yeah, if you multiply these two equations, mm, you'll get K E A R A equals K E B R B, right? So you could get rid of K and you have these equations. Okay, but that's exactly what we want, right? Because we know that E times R is just what? 1/4C um, T minus X, T plus X. Oh, sorry. It should be, yeah, where's definition? Yeah, we need to invert this relation. We see that, oh, sorry, speed of light should be here, of course. Yeah, because this is time. So, okay, mm, we have what? X divided by C plus T equals R, and um, T minus X divided by C equals E. Therefore, we have RE equals um, T square minus X square divided by C square. So that's exactly what we want. So this means C square TA square minus XA square is equal to C square TB square minus XB square. And that's precisely um, the interval um, between point 0 and this event in the reference frame associated with Alice and the reference frame associated with Bob. So that's how we prove the invariance of the interval with respect to the change of inertial reference frame. It's interesting to notice that, yeah, first of all, the Lorentz transformations, the symmetry group which preserves this type of quadratic form is uniquely determined by this relation. Yeah, but it's interesting to notice that there is a easy way to obtain the Lorentz transformation from here as well. And now we'll do it in the next video. So you could just click on it.